now that we completed all the derivative rules for general operations as well as specific types of functions, you might think, man, there's nothing left to do. Well, that's not entirely true. We have one other type of function to look at. Now, if you look at the title that I've given to this video, it says differentiating super exponential functions. And that's just really just my terminology. That's not a standard terminology. There really isn't a terminology for the type of function that we're going to look at, right? Now, let's say, to kind of give you an idea of what type of function we're actually looking at, okay? So we have a basic power function here, right? And we can extend this power function by having not just the x as the base, but we could have another function. So we could have something like f of x raised to the nth power, right? And we know, okay, yeah, we need to do the chain rule. So the chain rule in combination with our product rule, and I'll just kind of write it down and say, if we had to differentiate this, so the derivative of something like this, f of x to the nth power, would be n times f of x to the n minus 1 power times the derivative of the inner, which would be f prime, right? Right, so we can handle that. And then, of course, we have our exponential function, right? So we have our exponential function. In fact, let me not even write it with base a. Let's just say because we have our change of base formula, so technically we can convert anything to base e. But this you would say is our basic exponential function, right? But as we've seen in many instances, it's not just the basic e to the x. It might be like e raised to some other function, right? And again, because we have a basic rule for differentiating the exponential function, and because we have the chain rule, we can differentiate something like this. So the derivative of e to the f of x, well, the chain rule says this will be e to the f of x times f prime of x, right? So right, yeah, we can handle these extended power functions or these extended exponential functions. And again, the thing that really distinguishes these is that all the variables right here are in the base. So you have whatever your f of x is. It could be a quadratic, or it could be a trigonometric function, anything like that. But then it's raised to a constant power. You flip it around, now you have your constant base, and you can have, a variable exponent. You could have like a x squared up here, or you could have a sine of x up here. And again, we have a technique or a process for differentiating it. But here is now the question that I pose. What if you have a function that looks like this, where you have f of x raised to the g of x? How do we differentiate this? When it's neither a power, right? It's not a power function because the exponent isn't a constant, and it's not an exponential function because the base is not a constant. So what do we do? Well, it turns out there are two ways we can handle it. And in a sense, what I'm going to do is do it generally with this f of x raised to the g of x power, right? And then kind of highlight two different processes that you can take for finding the derivative, and then look at some specific examples. So when we do it generally, we are going to come up with like a formula, and it's not really a formula that you want to memorize. I'm not all about memorization um, at all. But in coming up with that formula, we will have illustrated a process that can then be used, right? Okay, so here is version one of the solution, right? So part of the difficulty here is that you have a function that's raised to another function, a power. That's a function, right? Well, we know because of a certain property of logarithms, if I took the log of both sides, and I'm going to use my ln since that's our natural log. So if I take the log of both sides, and it looks like this, right? And then, so now I have something that's implicit because I no longer have the y isolated. So in fact, what I'm going to do is write this in our kind of a implicit form, saying that, okay, now I have the log of y of x. And then over here, I'm going to use the property of logarithms that allows me to take this power and put it in front of the ln as a multiple, right? So take the g of x and put it down. And that's why we take the log, because it allows us to bring this power down, and we no longer have that issue. But what we do have now on the right hand side is a product, right? We have a product here and we have a composite here, right? So now let's differentiate implicitly and see what happens. So we're going to differentiate again with respect to x. Let's see what happens. Well, we know the derivative of ln, or natural log, is 1 over, and then it's 1 over y of x, and then the chain rule says I have to multiply by the derivative of y. So that's dy dx, right? So that's what I have on the left-hand side. On the right-hand side, I have to do my product rule, so the derivative of the first times the second plus the first times the derivative of the second, but then there's another composite. Like on this side, I had the ln of y. On this side, I have the ln of f, but it's the same kind of form. It's the same type of composition. So the derivative here is 1 over f of x times f prime of x. All right. So now, as in every implicit differentiation problem, we isolate the dy dx, and to do that we multiply both sides by y. That will cancel out this 1 over y. So then this entire expression here is now going to be multiplied by y of x. So let's write that down. So dy dx is equal to y of x times everything that I have here, right? Now there's not much we can do to simplify this, so I'm just going to write down the g prime of x times the ln of f of x. Now this I can write as a single fraction. In the top, I'll have g of x times f prime of x over f of x, and that's in the parentheses. So that is the monster of a derivative. But we're not quite done yet, because remember, let me remind you, the original function y is equal to f of x to the g of x. So what I can do is I can replace y with f of x to the g of x. And then I can get my, essentially, again, this is a formula, but it's not the type of formula that I would say just, memorize. I think more importantly, it's the process that we're doing here. So we have this raised to the power g, and then everything in parentheses gets brought down, right? Told you these functions, they're tricky because they're neither power nor exponential, right? And there we go. So that's what it looks like. And this process here, because this process started with taking the natural log of both sides, this process here is called logarithmic differentiation, right? Right. So if we didn't use the ln, then it would have been, we would have had to use something else because we couldn't have differentiated the f of x to the g of x directly, right? We would have to do a process like this, right? So let me write that over here. So this process is called logarithmic differentiation. Now, why do we use the logarithms? Because it allowed us to take that power down, right, and make it a product. All right, so that's one form. Now it turns out, and this is kind of a general thing, but it tends to be pretty spot on. If you can do a process with logarithms, chances are you can do it with exponentials as well. So I'm going to solve the same problem but a different way using e. Well, I'm going to still use the ln, but I'm going to use it in a slightly different form. So again, let's remind ourselves what our difficult function is, something like this. Now, recall there is a change of base formula, right? That if we have something that's a to the b, this can be written as e to the ln of a to the b, which can then be written as e to the b times the ln of a, right? We used this change of base formula when we were deriving the derivative for a to the x. We converted it to base e because base e is the easiest base in which to do calculus, right? So we can actually do that and convert this to base e, right? And then it will be kind of like an exponential function, but the exponent will be slightly complicated. So I'm not going to make it, it's not going to become implicit. It's still be in the form y equals, but on this side now, I'm going to apply this change of base formula. So it ends up looking like e to the ln of f of x to the g of x, so all of that. But then we can take the g and put it in front of the ln, right? So it looks like this, g of x times the ln of f of x, right? Nice little exercise in change of base. But now what we can do, so this is kind of like an extended exponential function. The exponent involves a product, right? So at some point we are going to have to do the product rule, just like how we did the product rule in the first solution, right? So let's see what we can write down for the derivative. The derivative of e is going to be e. So this comes back. So we have the e to the g of x times the ln of f of x. And I just want to pause before I write down the rest of it, because then the chain rule says we have to multiply by the derivative of this inner function. Notice the g of x times ln of f of x, the function that we're about to differentiate, we did that earlier. It's the same expression right here. It's the same expression right here. So it's going to be the same thing that we did right here, right? So let's go ahead and write that down. So it's times the product. So the derivative of g is g prime, and then ln of f of x and then plus the first times the derivative of the second, which is the 1 over f of x times f prime of x, right? So that's exactly the same expression that we had earlier. And then, well, notice all these things here are equal. All these things here are saying the same thing, just in different forms, right? So what I can do is I can simplify this and go back to the f of x to the g of x form, right? And then what we have in parentheses, that's, pretty much the same thing that we had at the end of our first solution. So we have g prime of x times the ln of f of x plus, and then I'll write this as I did earlier as a single fraction, g of x times f prime of x over f of x, right? And that's the derivative. So there are two ways you can do this. Again, you can use logarithmic differentiation or you can use your change of base formula. Either way, you can't get rid of the ln, right? It's just a matter in what form does the ln show up, right? So let's do maybe a couple examples of this, right? And again, I'm not just going to write down the formula. I'm going to go through the process, and maybe what we will do one example using logarithmic differentiation, and then the second example using our change of base formula for exponential functions. All right. So what do they look like? So that you'll be able to recognize them. Well, here's a simple one. You could have something like y to the 2x plus 1 raised to the x squared power, right? You have a linear function, right? So that's definitely not a constant. And it's raised to a quadratic function, which again is not a constant. So this function is neither power nor exponential, right? So let's use logarithmic differentiation for this one. So take the ln of both sides. And as soon as I do that, I'm just going to write it as y of x. I mean, I know what's going to happen because of the chain rule. And then once I take the ln of this side, in fact, let me go ahead, I'll do this side in stages. We do this, and then use the property of logs that now allows me to take the x squared and put it in front and make it a product. So it's no longer a power, it's now a factor. So we have the ln of y of x, and then that's equal to x squared times the ln of 2x plus 1, right? Now we're going to differentiate implicitly. So when we differentiate both sides with respect to x, what do we get? Well, the derivative of the ln is 1 over, and it's 1 over the y of x, but then the chain rule says I have to multiply by the derivative of what's inside. That's dy dx. And then on this side, do our product. Well, we're going to have to do a product and a chain rule here. So the derivative of x squared is 2x times the second, which is the natural log of 2x plus 1, and then plus the first times the derivative of the second, which is 1 over 2x plus 1, and then times the derivative of what's inside the ln, and that is 2, right? So this, I'll just switch it back to y. So we have, and then multiply both sides by y. Let's do that in one step. So dy dx is equal to y times this entire thing, right? So we have 2x ln of 2x plus 1 plus, now we can multiply these fractions. We have 2x squared over 2x plus 1. And then many times when our function is given in terms of x, like in this explicit form, we would like our derivative also to be in explicit form. So dy dx is equal to this quantity, because that's my y, 2x plus 1 to the x squared, and then times, again, everything that's in parentheses. So the 2x ln of 2x plus 1 plus 2x squared over 2x plus 1, right? And again, it certainly is not something that you would, just kind of be able to look at this and tell, unless, again, you just kind of memorized that formula um, from above. But I think more than, memorization, I think knowing the process, knowing why we do what we do at each step, that is key, right? Right? Knowing what we can do and what we're not allowed to do. All right, let's try another one of these. And let's do an example that involves one of our transcendental functions. So let's say we had something like sine of x, but then it's raised to the ln of x power, right? So something like this. It just looks strange sometimes when you see this, but I mean it's a well-defined function. Well, the domain is not all real values for several reasons. Clearly, the ln poses a problem, right? Our x can't be negative. And the thing with these, remember, with these, like what I'm calling super exponential functions, you still don't want something negative in the base. So we would have to rule out all the values of x that would make the sine of x negative, right? So figuring out the domain of these functions, they're not necessarily a walk in the park, but our goal is to find out their derivatives, right? All right, so let's look at this one and see if we can apply the change of base formula here. So changing it to base e, it becomes e to the ln of what I have right here. So the ln, let me switch these to parentheses and then have the square brackets there, right? So we have this to the ln of x. So we have lots of ln's here. But the key is I can take this ln and bring it in front, right? So let's do that. Let's bring this ln and put it in front of this ln. So y is equal to e to the ln of x times the ln of sine of x, right? And then now the base is constant. It's base e. So we can utilize essentially our extended chain rule extended exponential rule using the chain rule. So dy dx will bring down the e to the ln times the ln. So all of that comes down. And then next up, we have to multiply by the derivative of the entire exponent, which involves a product. So we have to do our product rule. The derivative of the first factor in the exponent is 1 over x. So it's 1 over x times the ln of sine of x, plus the first, which is ln of x, times the derivative of the second. It's another ln, but it's also a composite. So we have to do 1 over the sine of x, and then the derivative of sine is cosine. So we have the cosine of x there, right? Man, this really, again, looks like such a strange function. All these ln's and so forth. But the thing is, this first part, right, is exactly where we started, right? So we started here and we converted it to base e, and now just for simplicity, we'll go back to this form. So what's in front of the parentheses here, this factor is the sine of x to the ln power, right? And then let's see here, I can write this as a single fraction. the numerator is the ln of sine of x, and then that's over x. And then over here I have the ln of x times, now cosine over sine, that is cotangent. So we can simplify this just a little bit by replacing it with the cotangent of x, right? So this one, I mean, yes, it's still, quite the looker, right? But it's not as bad. And again, it's one of these things where when you see it for the first time, it's like, whoa, I never thought I could do all that, right? But then, you go through it and you realize that, as you carefully go through step by step, you realize that it's not that um, overwhelming a process, right? It involves a couple key steps. It certainly involves multiple, in this case, uses of the chain rule. Again, and we're just seeing just how prevalent the use of the chain rule is, all right? But that's our look at these special functions. I call them super exponential functions. You can give them some other um, fantastical name, or you could just say, they're f to the g, just a function raised to another function, right? Regardless of it, I hope this video has helped and, made you think about functions in maybe a slightly different form, right? See you in the next video.